And we move on to G484 homework booklet question 9. So we start off with the ideal gas equation. It says it may be written as PV equals nRT. Of course it's maybe, because that could also be capital N K T. They've written it that way. State the meaning of the terms N and T. It's a lowercase n. Lowercase n is the number of moles. The way I remember that is, I know it's a lower or an uppercase n is number of moles or number of molecules. The number of molecules is always going to be the bigger number, so that gets the big N, if you like, the big letter N, the uppercase letter N, leaving me the smaller number, the number of moles, as the lowercase n. T, the key thing is they don't just want you to say temperature. Okay, temperature would not get you the mark. You need to say it's the absolute temperature or the thermodynamic temperature or the temperature in Kelvin. You can say that how you like, but you need to make the point that it is that type, if you like, of temperature. Moving on to B, we've got a diagram showing a cylinder containing a fixed amount of an ideal gas. The cylinder is fitted with a piston that can move freely. The gas is at 20 degrees. The initial volume is that. Figure 9.2 shows the cylinder after it's been heated up to 90 degrees at constant pressure. So it's at constant pressure. So explain, and here's the key bit, explain in terms of the motion of the molecules. So you're not going to get anything if you start using PV equals nRT, or PV upon T is constant, or that PT is constant. That's all may be true, but it's not answering the question, which is to explain it in terms of the motion of the molecules. So what's going on? As I heat it up, the molecules move faster. That's going to give me a greater momentum change for each collision. So if I'm going to try and keep the pressure the same, what I've got to do is to reduce the number of collisions each second. And how can I reduce the number of collisions each second, and therefore keep the same or keep a similar total momentum change each second? I can do that by increasing the volume. So that was the 3 steps of logic there. This statement here, there would be more collisions, really should say there would be more collisions each second if the volume remained the same. Maxing out at 4. So as I say, molecules moving faster, that would give us more collisions each second. Each one certainly has got a greater momentum change, so to maintain the pressure, what we need to do is to reduce the number of collisions each second, and the way we can do that is by increasing the volume. Moving on to part 2 of that question, calculate the volume of the gas at 90 degrees C. They've absolutely got you here. With these gas law questions, you must, before you do anything else, get into Kelvin. You're getting 0 marks if you don't get both of these temperatures into Kelvin. So I've done that as a separate side calculation, the way I used to recommend you do a separate side calculation of cross-sectional area when we were doing Young's modulus, for example. And we're a fixed pressure, so why not use V upon T is constant, and so I've got the initial volume there from the question divided by the initial temperature, the 20 degrees C, which is 293 Kelvin, and that must be equal to the final volume divided by the final temperature, 363. If you then just do the arithmetic on that, that takes you to that value of 1.49 times 10 to the minus 4, just multiplying up by the 363 on the bottom on the right hand side. C then is saying that the mass of each gas molecule is that value. Estimate the average speed of the gas molecules at 90 degrees C. And what we're doing here, they're testing, can you remember that the average kinetic energy is 3/2 kT. Half times the mass times the average of the velocity squared is 3/2 kT. So all we're doing then is lobbing some numbers in. We've got a half times the mass from here is v squared bar, 3/2 k from the formula booklet, T at 90 degrees, 393. Now, on this occasion, if you use 90 degrees, they've already penalised you for using 90 degrees in part B, so you can have a couple of the marks, 2 of the 3 marks for using that. that is okay. Again, if you fail to square root at the end, you get 2 marks, but assuming you can do the arithmetic from that point there, working out v squared bar and then rooting that, you end up at 565 meters per second. So at 90 degrees, those gas molecules are whizzing around at 565 meters per second. G484 homework booklet question 9.